Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about the simplest radical form. Alright, we've been talking about exponents and radicals, and now we're going to talk about even more radical rules. Okay, so the first radical rule that we will discuss is the nth root of a to the n. We could rewrite that if we wanted to as the nth root of a, put in some parentheses, and raise the whole thing to the nth power. Either way it is written, it is equal to a. All right, the second rule. The nth root of a times the nth root of b can be rewritten as the nth root of a times b under the same radical because they have a common index, the index of n, for both of the factors here. Remembering this is a multiplication. We keep the multiplication under the radical with the same index. Why can we do this? Well, we've already talked about the fact that we can do it this way. Look at it this way. Writing the radical as a fractional exponent. In each case, we have a to the 1/nth times b to the 1/nth. And we can rewrite that as ab to the 1/nth, which means we get back to this. Okay? Our rule number 3. For rule number 3, we have the nth root of the nth root of a. Yes, you will see some nested radicals. But all you have to do in this case is to take those two indices and multiply them. That product becomes your new index, and the radicand is unchanged. Why is that? That is because, okay, if we rewrote the inside there as a to the 1/nth, okay, and then raise that to the 1/mth, and when we have that situation, we simply multiply our exponents. Okay, and we can write that in either order, making it, if we put it in alphabetical order in the exponent, which we often do, and because of our rules of exponents and what we talked about the last time we were together in class, that can be rewritten the way it is originally in the rule there. And now one final rule. Rule number 4. Okay, not the final rule for the course. Sorry, you don't get out of it that easily. Our final rule for simplifying radicals is this. If you have a fraction composed of the nth root of a over the nth root of b, you can have different things under the radicand as long as you have a situation where the index of each part, the numerator and the denominator, is the same. Then you can rewrite it with that same index and the entire fraction under the radical. So the entire fraction becomes the radicand. All right? As long as b does not equal 0. So if b does not equal 0. Okay? Now, why is that? That is because if we look at our rules that we've used before, a to the 1 over n over b to the 1 over n is the same thing as a over b raised to the 1 over n. Okay? That's the justification. Here's the rule. Okay, I'm going to clean this up a little bit and make it a little bit smaller and give you some actual examples which will help you understand this. Okay, let's make this smaller. Keep it in place because we will need this. And just to make sure you are familiar with the terms I'm using, here is a radical. The symbol itself, once again, is called the radical. The number here above the little stage of the radical, you might call it a stage, is not called the indents. It is called the index. Okay? And the number under the radical is known as the radicand. Okay, and I'm going to make that smaller and also leave it over here as a reference. Now, moving back to my white pen. All right, here's an example, and I'm going to number these examples as the rules are numbered. So here is example 1. These are all of the examples. Okay, so example 1, you might see the 4th root of 15 to the 4th. So here are the index and the power under the radical are the same. Therefore, this is just equal to 15. And we did that before in a previous lesson. Okay, so number 2. 2 examples for this second rule. First example, I'll label it A, will be the cubed root of 5 times the cubed root of 2. So according to the rule, since they have the same index, I will use that same index, write the radical, and then write 5 times 2 equals the cubed root of 10. Could you go from the original problem to this? Yes, but then I'd have no idea how you did it. So please show your work and give me this little intermediate step so I know you just didn't copy something from the back of the book. It will also help your understanding of the whole process. Okay, example B. The 5th root of 4 times the 5th root of 8. And notice you don't see any symbol in between here. That means it is a multiplication. If it were division, of course, you'd see a division bar. If it were addition or subtraction, those would be written in there, so assume it is a multiplication. Therefore, because of rule number 2, we can put it all under one radical with the same index. 4 times 8 equals the 5th root of 32. Okay, you probably remember also that the 5th root of 32, or 32 itself, is equal to 2 to the 5th, which is 2, according to our first rule that we've written. Okay, example number 3. Once again, these are examples for rule number 3. I'm going to give you 2 of them. Let's look at the square root of the cubed root of 7. According to the rule, remembering that there's an understood 2 here, this is actually, our answer will have an index of 2 times 3, and the radicand will remain the same. Leaving us with an answer of the 6th root of not 7, or not 6, but 7. Okay? There's my little bar for my 7s. All right, example B. I'm going to go ahead and use the same nested radicals. In other words, I'm going to use the square root and the cubed root, and I'm going to do it with 64. And yes, at this point you could say, well, the cubed root of 64 is 4 and the square root of that is 2. But I'm giving you a simple example that you can check in the way I just mentioned to show you how to apply the rule. Okay, so the same thing, this is going to be 2 times 3, and the radicand will be the 64. So we have the 6th root of 64, and from above you saw that 32 was equal to 2 to the 5th. That means that 64 is equal to 2 to the 6th, which is 2. All right, let's make this smaller so we have some room for examples for number 4. for rule number 4. All right, number 4. Let's take a look at the square root of 27 over the square root of 3. 27 is not a perfect square. It doesn't have a square root that you can just pull out of there. You could simplify it, but let's look at another way to do this. Using rule number 4, we would keep the same index, which is our understood 2, but we would put a fraction under the radical, like that. 27 becomes the numerator, 3 becomes the denominator under a single radical. And now that we have it that way, we can do 27 divided by 3 is 9, and the square root of 9 is 3. Okay, so that was example A for that rule. Example B. Let's take a look at that. Let's look at the cubed root of 10. Let's see if I can move this whole thing up a little bit. The cubed root of 10 over the cubed root of 16. Using the same rule, we'll take the same index, draw the radical, 10 over 16, and now we can reduce this fraction. Okay, dividing both the numerator and the denominator by 2, we get 5 over 8. Okay, now we're going to use the same rule, rule number 4, in the other direction. We're going to break this into 2 separate radicals, one in the numerator and in the denominator. Why in the world am I doing that? Well, I don't know what the cubed root of 5 is, but I do know the cubed root of 8 is 2. And now I have gotten rid of that radical in the denominator. Okay? I don't know about you. I can kind of understand 1/4 and 1/357th, but 1 cubed root of 8th, how do you even say that? It's a more difficult fraction to conceptualize, so we never leave a radical in the denominator. No radicals in denominators. And in another video in today's lesson, we'll be going over that. So this was video A. Make sure you move to video B next. Thank you.